So welcome. I guess this is the first CPM SOC event. So welcome to the club as well, or to the society. This is the first programming workshop of this term and of ever, and they'll be run every 2 weeks. I'm mainly presenting for this one. And some other people will probably present the other ones. We're planning to go until 7 today. It's fine if you leave earlier, I guess, and we might stay a bit longer if we're available for questions, general questions. I guess the main thing that you can do between the workshop 2 weeks in the future, which is quite a while, is practice solving problems on a practice problem set, and we'll give you access to that at the end, or some of you might have already seen that. And also for this particular workshop, I've decided we're going to split up into small groups, probably just 2 or 3 groups, because we don't have too many people here, for the last half an hour or so. So you can try a problem and get to know each other, I guess. And this will be recorded. I guess you don't really care because you're here. But you can watch it again, I guess. And of course you can ask questions. It's kind of hard to see the chat in Zoom when I'm screen sharing, but I'll try and check it. But also you can talk with your voice.
Yeah, we can read out the questions to you when they come in.
Yeah, sure, that'd be good. Slowly. There. Did I go over this already? Pretty much. I guess I'll just say it again. So I'll introduce what a problem is, because I should probably do that. And I'll give you some information about like what you can do with it, what you can do with competitive programming, like in your life. And the specific topics that I'll go over today are prefix sums, and I'll present a couple of problems to do with that, and time complexity, which is really important if you want to know whether your solutions are going to get marks or not, or points. And the group activity is probably going to take half an hour, and that will be smaller groups solving a somewhat hard problem. So what is a programming problem? This is an example that I found, and there's quite a lot of text on the left, and you can read it if you want. It's not very interesting, but yeah, it's phrased as like a word problem, but it's pretty much just asking, you start at Sydney, you take some route to go to Perth, then you take some other route and go back, and each one has a number associated with it, and you want to try and get the highest sum. So hopefully it's pretty obvious that this question is just asking to, given 2 numbers, find the sum of the largest 2. Him working, yes. So in this case, you would take these 2 and you'd get 1,200 points. And because it's a programming problem, we write a program which does this. So we're pretty much just writing like a mathematical function that takes 3 numbers. I guess we can use this, takes 3 numbers and spits out the answer, right? And then you'll submit this program to a computer, to a judging computer usually, and they'll pretty much just, they have a bunch of possible values of X, Y, and Z. They'll put them, they'll run your program given these given their certain values, could be 500, 300, and 700, or 1, 2, 3, or whatever, and make sure that you have the right answer for those usually hidden inputs. And if you have the right answer on all of their hidden inputs, then they consider your program to be correct, even though it might not be correct on every single input. But usually the data is designed so since you don't know it, you pretty much have to have a solution that works for any input. Okay, I have this slide because I should probably tell you why we're doing this. The main reason I do it, I guess, is to learn, practice, and enjoy it, but mainly enjoy it. Hopefully you will enjoy it as well. But it's also good just if you want to get better at programming, probably hacky programming, but programming nonetheless. And competitions, obviously it's in the name. Hopefully you find them fun, but you don't really have to be a competitive person or want to like win at everything to enjoy this. And I put in technical interviews. I've never used competitive programming in an interview, but maybe some more of you will think that you should come again if I say that it will help you get jobs or something. And speaking of competitions, here are a bunch of events. There's a lot of them. The main one at UNSW, I guess, which you can enter if you get some experience. I don't know too much about it, is ICPC. There's probably people who know that better than me, but I'll draw your attention to some other ones. So I think Google Code Jam is starting in a month or so. That's fairly entry level, so I think it's worth having a go at. If you're here today, I think you might as well have a go at that. I think Hacker Cup's a bit later in the year. I don't know what Amazalgo is. And look out for these. They should be coming fairly soon. The first one should be in the next couple of weeks, run by UNSW, or run by our societies. And there's heaps of just like hobby programming websites that you can try. Codeforces is very popular. That's the training site for high school informatics. That's for the US. And if you particularly want interview stuff, then I guess these two are good. HackerRank and LeetCode. Okay. Got through that quite quickly, but I don't really know how much experience everyone has, so I'm going to make a poll that says, do you want to see how you can submit to a judge and write a trivial program to add two numbers together and read the input and all that and test it? And it seems that I have to stop sharing. So I think the Zoom poll should be running. So pretty much if you've submitted C++ to any contest before, you should probably vote no. But if you're newer, maybe just starting out programming with your course, then vote yes. And if you vote yes, I'll still go over it at the end, even if not many people want to do it. Can people see the results, by the way? Oh, no, I think only I can see the results. Okay, I think everyone who should vote has voted. There's a question. Yeah, I'll get into languages in a bit, in a bit more detail later, but I think this society is pretty much just going to assume that you're willing, maybe not this lecture, but you're willing to learn C++. just because it is the standard language used. And the quick answer is it's faster, but I'll get into more detail about that hopefully later. Okay, we've got somewhat of a balance. I guess I'll share the results. Got a bit of a balance, a bit more people saying no. So I hope the people saying no aren't just the co-hosts here, but whatever.
The co-host can't answer the poll.
Oh yeah, okay, that's good. So it's fairly balanced. So I guess I'll just very quickly go over it, but I'm happy to stay around and go in more detail. Maybe just at the beginning of the group activity. All right, so you can start it a bit later. So this is a problem. And if you read it, then...
You might need to share your screen.
Yes, thank you. It's not a problem yet until I share. Cool. So this is a problem. And when you read it, the important thing is that there's the number A and B, and you want to see how much is lended in total. That's not very interesting. I guess it's more interesting that Tom has fat stacks of cash. But for this problem, all we're doing is adding the numbers together. Yeah. So I guess you can quickly look over this code. It's very, very simple. It's about as simple as it gets. And I won't go over it because most people, or just barely most people, know what this means. And if you know what it means, then that should probably make sense to you. If you're very new to programming, then I think there's a good way to get started just by going to this website. And it's pretty much all sorted for you. You don't have to set anything up on your computer. And then I guess if people want to, I'll show you how to submit to VJudge, which is the platform that we're using at the end. Okay, so I just went over that very quickly again. I'll go over it at the end if people want that. So now we're getting onto the main piece of theory for today, or one of the main pieces of theory, but probably this kind of piece of theory is more similar to what we'll be covering in later lectures, but obviously harder stuff and perhaps stuff that's built on this. And it's called prefix sums, and we'll motivate it like this. So Bob has an array of n numbers. Oh, that's thick. And I'll just draw an array like this. And Alice comes up to Bob and asks him questions. What is the sum of values from L to R? So if, I guess you can just not worry about the numbers, but he's just saying, what is the sum of values in this range? And if you've done any programming, then you probably think that's pretty easy, right? So if we have L and R, we can in C, or just in it to write pseudocode, just rub that blemish out. For I in the range L to R, I guess we'll set a sum to 0, sum plus, we'll call the array A, sum plus equals A, I, and then print sum or return sum, all right, print sum. But, and I'll get into more detail and more precision about this later. If our array is really long, say our array has 1 million elements, and Alice's questions are really annoying in that they like have size almost the size of the array, say like 500,000 or something. Well, that's not nearly, let's say 900 million, not 900 million, 900,000. Then all of Alice's questions, Bob will take a really long time to deal with them. About 1 million squared. And no computer can do this very fast. So we want a faster way to do this. And fortunately, there is quite a fast way to do this. And yeah, so we'll get onto it now. So this is some maths notation, which is completely unnecessary, but mainly here because I was testing how to use maths notation on the slide system. And what it's saying is that if you have a range of numbers in your array, let's draw the array up again, and you want to query what's the sum of this range, then you can ask, what's the sum of this range? What's the sum of this range? And you just subtract them. So you just take a minus b, I guess green equals a minus b. And that's what this silly notation is just saying. And maybe that's not obvious why that's useful at all yet. But why it is useful is because these two functions, I guess, if we treat the array as a constant, then they are variables, then they are functions only in this top value, L minus 1 and R. And that means, and like what's the domain of this function, I guess, is that top value can be anywhere between, well, for this one, it can be anywhere between 1 and n. This one can be anywhere between 0 and n. So we pretty much just have a function. We want to have a function that can take any number between 0 and n as input and output that range there. Okay. And here is me having more fun with the slide system. And it's a proof of the fact that you can add the things together, that diagram works, but that diagram is a way better proof, right? Yeah. So now here's some code, and I haven't probably motivated enough to get to the code yet. But what we do is, if we go back to this function, I'm calling it a function, but it's pretty much, we just want to make it an array such that A, let's not call it A, we'll call it P for prefix. P of some value in the array is equal to A1 plus A2 plus dot 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 plus AI. And then to calculate this value, all we have to do is calculate this value at R, this value at L minus 1, and subtract them. And then we found this very fast. We didn't have to like iterate over the whole range. We just had to access two values of this pre-computed P array. Okay, so back to the code. One thing that I've glossed over is how to actually calculate this P array. So, and that's fairly evident here in the slides, which is these 3 lines here. So what this is saying is the sum. So remember, they're called prefix sums because we're taking a range that starts at the very start, which is a prefix. And we're just, in these lines here, we're just saying the sum of this is equal to the sum of this plus whatever values in here. And I didn't write up a proof for that, but hopefully that's equally obvious, if not more obvious. Okay. One thing that is fairly important is what is the value of pre of 0. So you can see in this particular case, I've indexed them from 1. Probably most of us are familiar with the principle of indexing and like 0 indexing and 1 indexing. And by prefix of 0, I mean, what is the range that is not even a range? Which is just like pre of 2 will be the sum of these elements, and pre of 0 will just be like nothing. So that means we want pre of 0 to be 0. And probably a few of you know this, but in C++, if we declare that variable is global, then it'll be set to 0 for free. I guess if you want to make it more clear, you just set that. And then you don't need that to be true. And then all of this will follow as we want it to follow. Okay, so that's how we compute the prefix sums. And then these are the questions that Bob was asking or whatever. And if we go back to that formula a couple pages up, which was proven using the commutativity, what was it? Associativity of addition, then we'll see that we're taking P of R minus P of L minus 1. And this one's also 1 indexed. So it's pretty much trivial from that point. And I put these stupid brackets here so it would fit on the page. That's awful. So put that there in the very bottom left. Okay. That's pretty much the very basics of prefix sums. And there's a few more things you can do with it. I think since I'm going slightly quicker than expected, I might go over another application, which has a similar but fairly different idea. Okay, so now I'll go on to time complexity. I might come back to prefix sums later. And pretty much time complexity, what time complexity is formalizing what I said, or formalizing and generalizing what I said about prefix sums. And if you remember, I said we want to help Bob quickly deal with her questions. And we need to be slightly more rigorous with what quickly means. So the basic principle was, what have I got on my slides? Yeah, don't worry about that. So the basic principle is, if we want to do our operations fast, if we want to do our query operations fast, then we want to do them in constant time rather than time that's proportional to the size of the range. And in the worst case, the size of the range is the size of the whole list. So don't worry about what it says on the slide yet. But so our first crappy for loop had, I guess I'll write it like this, had n steps, up to n steps. Or if we really want to be like that, then it's r plus l, r minus l plus 1 steps. And this has a maximum of n. So each query could take n time, could take n steps of the for loop. So I guess query, the time of the query is big O of n. And I'm using a big O of n because we don't want to distinguish this from, the notation's a bit funny here, but I don't want to distinguish it. Okay, that's terrible, I won't use that. We want to say that these two things are the same function or the same set, depending on how formal we're being. So if we go back to that code, this one's pretty simple, right? Because, can you see my annotations? You can't, right?
Nope, I don't see anything on the screen.
Okay. Yeah, well, I did write on them before. I'll see if I can recover them, but I don't know. So this one's pretty simple. This first loop here, you still can't see it. Okay, I'll quickly stop sharing. See if I can refresh it. My annotation setup is pretty bad. Okay. Yeah, but you can see that, right?
Yep, we can see that.
Cool, thanks. I thought I just deleted. Okay, what? Okay. For some reason, my iPad doesn't sync very fast to this. That's fine. So, so this one, that loop, it goes over it exactly n times, right? So that's obviously n. Now this one, n exactly n operations. But this one, it has 2 operations per iteration of the loop, and so that's 2q, I guess, or big Q, whatever. And that one's also trivially n. And I guess if we change it to n for a second, because it doesn't really matter, say there's n queries as well, doesn't matter, then that will take 2n. But one thing that is very powerful, I guess in computer science and this and competitive programming, is we want to consider these as the same. And we want to do that because I guess a bad explanation is this won't take much longer than this, but it will take twice as long. But a better reason is if we run this in C++, it'll be quite fast. But if we run this on Python, then this line, an equivalent like translation of that line might take twice as long or something. Probably won't take twice as long. But if it gets more complicated, then it could take twice as long. Maybe it does take twice as long, I don't know. But the point is, we don't want different languages to have the same algorithm and have different different time complexities that we associate with them.
I think the main thing is that as n gets really big, difference between n and 2n is not that big compared to the difference between, say, n and n squared, right?
Yeah.
Because when n gets really big, n squared will get a lot bigger than n compared to like 2n or 3n or even 100n.
Yeah. So mathematically, that's how we justify it. I'm just trying to put it into some context of how it's practical, because you might think, oh, if our thing takes 1 million n, why should we call it the same? That's ridiculous. And I guess one motivation for that is differences between programming languages. And one of them, which is very similar, is if we implement the same piece of code, if we implement the same algorithm twice, it shouldn't matter how we code it really, or how many lines of code we have, how many steps we have, how many plus signs we have per line or whatever. All that should matter is what the algorithm is. So it should be independent of implementation. Oops, I'm skipping. Okay, so Dallas touched on this, and that's the formal definition of time complexity. You can like read it on Wikipedia or something. You can get way more formal than this, but we can use this to compare algorithms. So since where's my pen gone? There. Since we're treating these as equal, I guess I'll put a congruent sign. Since we're treating this as equal, and we're also treating that as equal to n plus 1. I don't know where my sentence was, but since we're treating these as equal, and mathematically, if we want to rigorize this, then we say as this as a ratio of this approaches 1, or approaches a constant number. So it doesn't depend on n as n gets really big. And if you're taking calculus or whatever, then you can like have fun proving these limits and whatever. But that's not the point. The point is, as Dal said, there's not really a big difference between n and 2n if n's really big. Yeah, so that's kind of a much more concise way of what I was trying to say not too long ago, which is that word operations was quite ambiguous, but that doesn't matter if we're using our way of defining time complexity and big O notation. Wow, both points showed up at once. Okay, so in simple examples, all we have to do really is take the number of operations for any definition of operations, and we take the fastest growing term. In this case, it's n squared, because n squared is faster than n by graphing or whatever, as n gets big. So get rid of any non-fast growing terms and get rid of constant factors. And then we have its class, I guess, in big O notation. So people can read that. I'll get rid of that. So, but maybe you can see that this kind of approach of just taking the dominating term and removing any constant coefficient might not work if we have functions that don't just have an addition of like terms like this. Like, I think this is kind of contrived, but I guess they should have the same big O complexity, but it's not a simple situation where you can do that. And you do that by taking limits instead. Okay, this first point is somewhat useful, but it's more useful to add to this something slower than something else if we have two algorithms, A and B, if I guess they're functions of n, but whatever. If this approaches infinity as t gets big, sorry, not as t gets big, as n gets big, then B is slower than A. And if it approaches 0 as n gets big, then B is slower than A, where t is just any function that takes the time, that takes the number of operations for any definition of operations. Okay, and so I've highlighted the fact that we care about the time complexity in the worst case. And maybe it's wasn't obvious from this example that we need to be quick. Like, we could have, like, what if all the ranges are really small? But if we go back to that very opening thing about how the judge does it, then the judge will have lots of cases that are intended to try and break your code pretty much. And some of them will have lots of big ranges in the prefix sum example. So we need to make sure that our code can handle them fast. Okay. This stuff about time complexity has gotten pretty theoretical, so I'll try and make it a bit more concrete now. I guess I'll put these examples aren't super concrete, but I'll explain exactly how we can use time complexity if we're trying to solve problems under time limits, which is, I guess, the application of that. Okay, so this is an example. I'm sure many of you could come up with a way of finding the maximum value of an array in order n as well, I guess. And yeah, I guess I'll ask if people want to put forward how to do that. So if anyone knows how to do that, then you can send a message. Yeah, so someone suggested max array, it's possible that I know this function exists in Python and it will take the maximum of the list. But I don't think there's an equivalent function in C++. Maybe there is. Actually, there probably is.
There is one if you use the standard library, and I think it's like max element, and then you have to use iterators, like begin and end for the array.
Yeah, cool. Okay, so there is. But that sounds a bit hard. And Donald suggested the way that it's probably implemented, and Sue has posted, in fact, the full code. And if you want to see the code, then I think Sue's is pretty good. Okay, we've got another piece of pseudocode as well. And so thanks to all of you. So pretty much we're just going through, we're storing some maximum so far, and we're updating that for every element. It's kind of similar to how we updated the sum every time. And if I very quickly transcribe it, I'll take, let me rubble this out. We initialize max to, we can initialize it to the first element of the array. I'll say negative infinity, and you can think about why we do that. And then for A in array. Max equals max. Okay, that's not good, but whatever. Max equals max A and max. Oh, wait, we won't use that. We'll actually use the comparator, which most people, I think, suggested. So if A is bigger than max, so if we have a new maximum element, then max equals A, and return max. So if we count the number of operations, like I was talking about earlier, we have one here, I guess. We have, I don't know, some people would count that as a line. I guess I'll count it, why not? So if we have, so the size of the array is n numbers, then that will take n. This check will take n. Depending on how many times that line activates, this could take up to n. So, and it could take 0 or 1, I guess, 1 or somewhere between 1 and n, maybe 0, I don't know. So we'll take somewhere between 2n plus 1. I guess that's a line as well, so 1. So 2n plus 2 and 3n plus 2. And we don't really care. In any case, from what I said earlier, this will reduce just down to big O of n, because all of these things are within a constant factor of each other as n gets large. Okay, so I went over that in quite a bit.
You just muted yourself.
No, the host muted me. Okay, I'm the host. I don't know. It said the host muted me.
Yeah, I think
That's
someone
okay.
muted you when they were trying to admit someone else.
Oh,
Like
it's
they
all good.
accidentally clicked the button.
All good. And if you're interested in like the C++ standard library, then you can look at what Jonathan's put in the chat. And that's useful. I don't think I'll ever use that, but just because this is easy to remember, even though that's actually quite easy to remember. But it's good to understand this, and I thought it was a good example for explaining time complexity.
Just as another side note as well, on the previous slide, we used minus infinity. In contests, they'll usually give you constraints on how large the values of n could be. So if the question says, for example, n is going to be an integer between minus 2 to the power of 10 and 2 to the power of 10, then you can use those numbers as the minus infinity or infinity. So you don't need to think about integer overflows or that sort of stuff. You don't need to use intermax from the limits library. You can just have a look at the constraints given to you in the question and then use those numbers as the values for infinity.
Yep, exactly right. And I guess I just put negative infinity there because not because it's practical, but because mathematically it's more correct if we want a flawless mathematical algorithm. And you could think what is the maximum of the empty array, which is an array with no elements. And the most sensible thing to assign to this is negative infinity, which exists as a mathematical object, but not really in code. Okay, I'll leave it at that, I think.
Also,
Yep.
so Isaiah had two different number of operations there, best case and worst case. Sometimes the best case will be a different O class to the worst case. So maybe the best case has one operation, the worst case has n operations. We will only care about the worst case because 99% of the time we'll only care about the worst case, because when you submit it to a judge, they will have hidden test cases that will make it as slow as possible for you.
Yep, absolutely. Yeah, this example probably didn't do justice to the point of that, but that's all right. Okay, so if you remember today's problem, it was we have some roots, and we have three roots, and we have three roots like this, and they each have a number associated with them. Not zero, that's just a variable, I guess, but they're all different. And we want to find the two largest values. And if we generalize this somewhat, not fully generalized, then we can add more roots, and we can still ask what's the biggest return trip that we can have. So what's the biggest sum of these two? And I'll leave that as, actually, I'll ask you, because people seem fairly engaged. So I'll ask that question, how to find the sum of the two largest elements in the array. And I guess while you're thinking about it, feel free to put it in chat though, while I'm talking. One way to do this would be to sort the array first. And I'll explain this in a tiny bit more detail in a minute. But sorting takes O and log n. I didn't put a base because the base doesn't actually matter, because by change of base law, it differs by a constant factor. But I guess I'll just put a 2 there, and you can think about why that is the fastest you can sort an array using comparisons. But that's a bit hard, so I won't cover that in too much more detail. But that's the fastest time you can sort the array. So we can simply sort the array, take the two biggest numbers. So I guess we'll take a of n plus a of n minus 1, and then we're done. But that has that factor there. And in any reasonable application, that probably wouldn't matter. But it's a useful theoretical exercise to work out a way to do it faster. Okay. Hopefully people are thinking about how to do that. I probably just won't go over it unless people have any suggestions within the next 30 seconds of how to solve that problem. Just because it's probably better that people think about it rather than me just spoiling it. Okay. So that's pretty much what I just said. You can sort a list of numbers, which just means you ensure that each element is smaller or bigger than the next. Not smaller or bigger, that's obvious, but smaller than the next, let's say. Okay, this is just a silly example that I chucked in as well. There's a somewhat famous problem where you're given an array of n numbers and you want to see if, I'll write some stuff out. You want to see if any three numbers sum to 0. In this case, I don't think any three numbers sum to 0. Is that even the problem? Yeah, it is the problem. Any three numbers sum to 0. If I add this number here, then if we take this number, and this number, then three numbers do sum to 0. And I will leave it as another exercise, which I won't go over at all, how to solve that in n squared. That's not too hard. Maybe you need a little bit of more knowledge than what I'll go over today, but it shouldn't be too hard. Okay, and as another exercise, you can try and solve it faster than n squared. And by faster than n squared, I don't just mean faster than n squared. I mean n to the 2 minus epsilon, where epsilon is greater than 0. So we solved it for epsilon is equal to 0. it's not hard to solve it with epsilon equals 0. You're going to try and solve it with epsilon greater than or equal to 0. Sorry, greater than 0. Okay. Okay, so I've gone through a few examples quite quickly. If you have any questions about that, then I know it's gotten probably a bit harder than it started out. So feel free to ask about that. So now I'll talk about how we apply this in contests. Okay. So, so in a problem, we'll get in a problem statement, it will usually say how long our program has to run, and often it's 1 second. So let's say 1 second. In a second. My pen's dead. No way. Okay, in a second. Okay. So if we have simple stuff like, I don't know what does simple mean, but like if we're just adding numbers together, then let's say we can add 200 million numbers together in a second. And this is very variable, but we'll just go with it. And maybe if they're more complex operations, closer to 50. And it also depends on the judging machine, the computer that's running your code. But we'll go with that. And so in addition to the time limit of the problem, you'll get some constraints on the input size or the numbers in the as values. So in the problem, we might say time limit is 1 second. 1 second, and n is less than or equal to 5,000. And what we want to be able to do is work out, okay, what does my time complexity? So what function of n is suitable for this problem, and which one is going to pass? And in general, if anything is too slow, so it'll be tested on a bunch of cases. If any of them are too slow, then you'll probably get 0 points, which is sad. So this is, I guess, equally important as the correctness of our algorithm. Because if it's really slow, then you'll be sad. And this is a kind of cheat sheet for that. I just chucked it together. The numbers are fairly random. And obviously there's leeway because of the machine and because, yeah, it just kind of depends. But I guess a very common constraint we'll get is 10 to the 5, which is 100,000. And oops. And 10 to the 5 is good because n squared algorithms will almost never pass. In fact, should never pass. And anything from n, like order n time, to n square root n, which we'll probably come across at some point in the workshops, should pass. Okay, so I'll just talk about some of these because why not? Some of the worst algorithms you'll see take n factorial times. I guess since we have a bit of time, I'll talk about this. So say we want to sort a list of numbers. So we have a list of numbers. And one really bad way to do this is just shuffle the numbers, check if it's sorted by checking if each number is less than the next one. And then if it's sorted, then we're done. Otherwise, keep randomizing until we finish. And I guess almost by definition of the factorial function, the number of different ways this could be permuted is n factorial. And the number of correct ways is 1. So we have a 1 in n factorial chance of guessing the right thing. I guess there's an extra n because each one takes n time to check. Wait, no, that's the wrong place to put the n. So each one takes 1 n factorial times to check on average. So we'll have to check n factorial things on average. And so that's n factorial times n. That's a really bad way of demonstrating that. But there's probably some problems that necessitate n factorial. That one, I guess you'll see if you optimize that, not for the sorting, because that was a stupid example, but many problems which can be solved in this naively can be somewhat optimized by that, even though, as you can see, it's 20, which is still really small. Okay, n cubed, I guess these are pretty self-explanatory. Maybe that one should be 5 times 10 to the 3. And maybe 10 to the 3 should be n squared log n-ish, maybe. And also all of these are upper bounds. So if you can find a faster algorithm where, like, if n equals 10, then obviously you can solve it in order n. Like for addition, where you can solve that in constant time, or logarithmic time if we want to be technical. But it's obviously fine to be fast. This is just the slowest your algorithm can be. Or one possible slow-ish algorithm that will solve the problem. Okay. And I guess, yeah, these are pretty self-explanatory. You probably won't see that one just because that's such a big input that usually competitions don't like having big input because it kind of depends on how you read the input. Okay. I'll look at Sue's response to that first exercise. Yeah, I won't look at it properly, but that looks just about right. So pretty much, good job, Sue. Instead of keeping track of the biggest number so far, we keep track of the 2 biggest numbers so far. And there's a few cases that we have to deal with, but pretty much we can, whenever we encounter a new number, we can make sure we still know the 2 biggest values, and then we just add them at the end. A problem is ever going to be non-deterministic. So does that mean a problem that will require a non-deterministic solution? I guess deterministic, there's kind of 2 definitions of deterministic, or of random. And I guess some algorithms can have like a somewhat random element to them. I guess a famous one's quicksort, which is a sorting algorithm, which I think has worst case time complexity n squared, but it almost always runs in n log n. It's non-deterministic in a sense. If you have some genuinely random way of picking an element, I think in quicksort, then it will be non-deterministic. So basically, yeah, sometimes non-determinism can help us solve a problem. But in practice, usually we just use a pseudo-random function, which is deterministic given a certain compiler and machine and whatever. So if we run the same piece of code twice, then we'll get the same answer. Yeah, for scanf, C and C out, you can use either really, but C and C out, if you want to make it fast enough to read big inputs like 10 to the 6 or 10 to the 7, then you have to add a few lines of code. But I think people will be familiar with scanf because it's also from C. I think C in and C out are from C++, maybe.
Yeah, they are. Yeah, there is a line of code, and there are some questions which have really large inputs that you will need to add in like 1 or 2 extra lines of code just to make sure your program passes the time limit.
Yeah. Oops. Okay. Non-deterministic as in NP hard. I guess probably you won't see them for a while, but there are some problems which maybe aren't solvable or are extremely hard to solve. At least whatever 50 years of computer science don't think that they can be solved very fast. And sometimes non-deterministic or pseudo non-deterministic algorithms can help you get big points on them. If you want to hear more about that, then I'll go into it later, but it's probably not the focus of this. Yeah. Okay. So I'll go over one more problem, and then I'll probably go over a bit more theory about prefix sums because we have time. So this problem, I want people to talk or chat about this problem because it's not trivial, not that trivial. So the problem is you're given an array of numbers. Yay, so many arrays today. This problem needed a character that does nothing. So I guess Alice thinks the number is 13 is bad. And we want to determine how many subarrays have a sum of 13. Okay. Okay, I might have made this example too hard for me to solve it by hand, but whatever. So in this case, if that's our array, n equals 5, that subarray sums to 13. That one sums to 13. That one sums to 13. That one sums to 13. There might be another one, I don't know. But let's just say the answer is 4, probably more. So I want to determine how many distinct subarrays have a sum of 13. Okay, there is a faster solution than this, but just for the sake of educational or instructional purposes, I want people to try and work out an n cubed or n squared solution to this problem. Yes, subarrays are contiguous, so they're just a range of numbers. So increment to the index by 1 each time until some right value. Yeah, so someone's, okay, I'm not gonna have space to do all this. Oh, that's all right, I can rub it out. But then people in future won't be able to see it, but that's okay. You get exclusive content at the live lecture. So yeah, all good. So the n cubed is pretty much a brute force. So we just try every range pretty much. And specifically, Joanna said we're going to try every size of subarray, and that works. So for size equals 1 to n. Okay, I'll start writing smaller, unless I've lost my screen share. Sorry about this. Okay. And I raised it for free, apparently. So I am going to do Joanna's first. So that's for size equals 1 dot n. And then I guess for all sizes, we kind of have a situation where we're testing that and that and that and that. And so one way to do this is to refer to this by the first index. So for first index, we'll call the first index I. Is an element of one. I don't know. For I is an element of, I'll get this wrong, but it's something like that, plus one. Maybe. Then for, I guess, numbers in I to I plus size minus one, ants plus equals x, and sum plus equals x, sum equals 0 here. And then, so now we found the sum of that range. And so we can find the sum of any range using this method. So this loop takes maximum time n. This loop takes, I'll use a different color. This loop takes maximum time n. This loop takes maximum time n, because size can be small, and this loop takes maximum time n because size can be big. Okay, so that's n cubed. Now I will erase this intentionally, because I usually erase it accidentally. Okay. So I shouldn't have erased it. Can I undo it? Yes. Okay. So someone else suggested I use a 2D array to record the prefix sums. So I guess prefix sums, I guess by the definition I've been going on so far, are a one-dimensional array. If you want to elaborate on that, because there's probably something correct in there, but I probably won't go into it unless you have more to say about it. But okay, I'll quickly jump to Joanna's. I think Yasiru has got a way to get this down to n squared. So Joanna says instead of our outer loop being size, we can kind of change that to there. So switch these two loops pretty much, and fix any indexing issues we have. I think it's not too hard to see that this will also take n cubes, pretty much just because we're still having 3 nested loops that each could take up to n time. Okay. So
yeah, Siri's got a n squared algorithm. If I'm thinking what he's saying is what I'm thinking.
Yep, I agree. So pretty much one thing that we can do is get rid of this loop. This loop is bad. And why is it bad? Because earlier in the lecture, I told you that you could do this faster than this. If you remember Alice and Bob, or whatever, then instead of adding up each element in the range, we can take the prefix sum at the end of the range, subtract the prefix sum at the beginning of the range, minus 1 or whatever, and then we have the sum of that range. So pretty much we can just prefix sum that whole thing. And that reduces all of this stuff down to constant time. So now we only have 2 loops, and now it takes n squared. Okay, are people happy with that? Or if you're happy with that, then you can keep thinking about order n, and I'll give you 1 minute to think about that, I guess, because it's a good one to think about, I think. And while you're thinking, I will rub this out and write some stuff. Yeah, let's change slide because I actually had that slide set up. I'll write it. I'll put that. I'll put what I had there. What was I doing? Okay, I'll have a look at what's happening. Add 13, subtract 13. So if we have 1, 2, obviously the number 13 is completely arbitrary. That's 5, 6, 5. So we add 13. I guess subtract 13 from every second one. -6, 6, 6, and then we're instead finding sums of 0 with that and that. I think if the array is getting bigger, then that kind of dies, does it? Maybe there's something there. If you want to put more details about that, then I'm happy to look at it. Okay. It's not cover all cases. It's something. Yeah, I think just intuitively, I don't think an alternating kind of approach is going to get where we want it. Get to where we want. But maybe there's something I'm missing, and you can keep following that line if you want. So just at a very quick glance, it looks like you have 2 nested for loops. Each of them take n time, or each of them have n iterations. So that would still be n squared, right? And if I haven't been clear, well, right now we're going for n because we could optimize that to that using prefix sum. Yeah. So Sue's is actually pretty much just prefix sum, except instead of actually computing the prefix sum array, which I kind of implicitly did before, she kind of calculates it as she goes, which is just as good a method, if not a better method. It's probably a bit less code. Two reference indices, jets. Yep, so Joanna has touched on an interesting idea. I don't think it's quite what we want for this problem. I guess I'll very briefly mention it and you can do your own research. And I think we'll probably be covering it because it's a very important idea. But if I'm understanding it correctly, we have an array. I'm gonna use this next slide. Should I use that next slide? Okay, I won't be silly. I'll just use the previous slide. Yeah, there wasn't. much except the stuff in the top right. It's not too important. Joanna's idea. We have two kind of pointers. I'm calling them pointers because this is, or because they're called pointers in C++. Or C. But also because this technique is called two pointers. And it's pretty much to determine some stuff about ranges. We start with these two pointers and we move these, we shuffle these across, and we shuffle them across in some order such that we count a bunch of ranges, and then eventually they reach the end and we've done some stuff. This is a good thing to think about whenever you're thinking about maybe, pretty much subarray problems. In fact, it's possible that there's a method using this for this problem. But I think there's a probably easier way to do it, and that involves, there's a probably easier way to do it, which we'll get to eventually, I guess. And this way, if we're only considering this as a candidate range, then it still takes constant time for every range. Even if we increment this, it will still take constant time to get that. And it's actually possible that we can have a really bad array that actually has almost n squared thingos, and that's this. So this one, there's a whole bunch of ranges. Pretty much any range that intersects this element is going to add to our count. So usually this kind of approach will only count up to, it will take a constant time per range, and this could take up to n squared. That's why I'm going to stay away from that. But that's a good idea. And actually, it's possible that you could get that out. And actually, I'll think about that after I look at this. Yeah. Okay, I think Yasiru has pretty much got my intended solution. Sorry, I won't think about that's two pointers or sliding window technique anymore. So in this somewhat graffitied box here, let's make the box a bit small. I've pretty much stated the condition that we had, which was we add 1 to our count whenever we have a range which has sum equal to 13. That's an L, that's a 1. And that's I don't know, just a shorthand, even though it's not that short for that. And pretty much what we want to do is not use this massive for loop to calculate that. And I won't phrase it exactly how Yasiru has phrased it, but I'll do it similarly. So if we have a prefix sum here, let me think of this. Yeah, if we have a prefix sum here, then it's expensive to check all of these. What if we could do them all in one go? And so what we do is, I guess it's kind of trivial, but you can rearrange this formula. So pre-R equals pre-L minus 1 plus 13. So pretty much all we're doing now is when we're at this index, we check how many previous values are 13 less than this value. And I guess if all the values are small, then what we can do is have some like array that has count of x, which counts how many prefix sums, so how many of these things exist at a certain value. So the count of x equals number of I such that prefix of I equals x. That's probably barely visible, but yeah. So, and so pretty much we just, whenever we come up with a new number, we calculate its prefix sum, and we check and we look up in this count array, we check count of pre-r minus 13, and we see how many values exist here. And then we add that to our total answer. So I guess the important ideas here were, we're using what we calculated here, well, using the prefix sums here. We're building up our count array as we move along. And every step of the way, we're checking how many ranges exist that end here. And we're doing that fast using this. You can implement that as a hash map or an unordered map, or you can just use an array of Booleans. Rather than an array of Booleans, and an array of counts. And I think that ends up being equivalent to Yasuru's suggestion, which was to add 13 to each element and kind of have two arrays, which is pretty much what we've done here. Have two arrays and check against all of these. Okay, this was much more involved than anything else, or any other problems at least that I've gone over today. So yeah, if there's any questions, put them down. I said I would talk about more applications of prefix sums. I guess I'll put that up as an option. Make a poll now, because now we're planning to do the group problem solving. Unless people don't want to do that for whatever reason. Oh.